In the previous modules, we had been looking at the principal component method as a technique for dimension reduction. What we will begin with today is the factor analysis method. This is another dimension reduction method and is very widely used in psychometric studies. What the factor analysis method does is to identify a number of factors which gives rise to the given variables. So, if we can find some inherent factors which are smaller in number to the given variables, which actually influences or perpetrates into these variables, then we can just be looking at those factors instead of the variables. That would generally be a smaller number of factors or variables to look at. So, that way we can make a dimension reduction. And in this lecture, we would be looking at how we can model in a factor analysis setup and what are the conditions that needs to hold and how can actually use the model. I will give an example for this, and in the subsequent classes we will be looking into greater details of the factor analysis model. An alternative technique to the principal component is the factor analysis. This is also a dimension reduction technique, but as you will see that it works in the reverse direction of the principal component. And in this case, what we look at is what are the underlying characteristics which affect the variables. So, there may be a very large number of variables, maybe 50 variables. However, this 50 variables may be given rise to by small number of variables, say 5 or 6. So, if we look at the underlying characteristics of these variables and if we can identify them, we will call them the factors. Then if we look at these characteristics, maybe instead of looking at all the variables, we can just look at a few of these characteristics or factors. These factors may be specific to a variable or common to several variables. We will be more interested in the factors which are common to several variables, because that will actually enable us to reduce the number of variables. Let us look at an example first. As we all know that when you are in school, you need to learn a number of subjects, and this may include vernacular, English, mathematics, physics, chemistry, biology, history and geography. And at the end of the term you have a test. When you do the test, what exactly are we trying to look at? We are trying to look at the student's aptitude. Now, if you look at this 8 subjects, this 8 subject requires different types of aptitude. But how do you know whether a student is good or bad? What we do is we take the sum of the marks and then rank the students or whatever, we grade them, etc. But we take the total of this marks that they get in the different subjects. But obviously, this will lose several features. For instance, a student may be very good in mathematics, but cannot remember a lot about history or geography. He may not be a creative in the sense that he is not good in the languages, because language needs a little bit of creativeness. Okay? So, logical reasoning, creativeness, memorization capabilities, these are some of the factors that go into explaining the scores in the different subjects. So, if you just concentrate on these 3, so can we subdivide the subjects according to these 3 criteria: memorization, creativity and reasoning capability? Which subjects requires which of the characteristics? So, if you know that, we can identify students in a much better way rather than summing up their scores. We can see their capability score in the sense of reasoning, in the aspect of creativity and in the aspect of memorization. That would give us lesser number of variables than 8, but will not bring it down to a single variable where we lose all the features. Mind you, the single variable itself is a sort of a principal component in the sense that it takes a linear combination. but we do not look at it that way, because it just takes in the total variability into one single variable. Now, the number of such factors should be obviously small compared to the number of variables, otherwise the whole purpose itself is defeated. And we can statistically find out how many factors would be necessary to give a reasonable explanation, taking in account a major part of the variability in the data set, as we did for the principal component methods. One thing that we cannot do basically, and we will see this later on, is that the interpretations of the factors. We can identify that there are 3-4 factors, but naming them, as I just did when I said memorization, creativity, etc. The one thing that we cannot do is the interpretation of the factors. This is because we can tell you that okay, there are 3 factors in it, but which factor is creativity, and calling it creativity, calling it memorization capability or reasoning capability is beyond the scope of a statistician. It has to be done by the subject expert. We can say that there are 2 or 3 major factors which influences. We can identify these factors, but what the name of this factor would be and how you interpret the factors, I think is better left to the subject experts. Now, let us discuss in detail a factor model. Suppose there are p general factors f1, f2, fp, and obviously p is to be much smaller than m, which is the original number of variables. So, we had x1, x2, xm as the number of variables, and now we are trying to explain it through p factors f1, f2, fp. The first variable x1 is given by mu1 plus L11 f1 plus L1p fp plus epsilon 1. Mu1 is the constant here, and we will see that it plays the role of the mean, and the Lij's are basically the coefficients. So, this gives us a linear combination of the p factors, which gives us x1. Similarly, we can have x2 explained by another combination, xm explained by a mth combination. So, we can have different combinations leading to the m different variables. One thing that you can note here is that unlike in the principal component, we are going the other way around, that is, we were taking linear combination of the x's to get the principal components. In this case, we are taking linear combinations of the factors to get to the x's themselves. So, it possibly is a reverse direction that we are looking at. This Lj1, Lj2, Ljp are referred to as the factor loadings for the jth variable. The coefficients are referred to as the loadings. So, if you look at x2 for instance, then L21 is the loading of the first factor in x2. If L2p would be the loading of the pth factor. The epsilon 1, epsilon 2, epsilon p can be regarded as an error in the model. Okay. But in this case, we will not call them errors, we will rather be calling them specific factors, and we will explain why we call this specific factor. Now, one thing that we should note here is that if you look at the first elements, those are the mu's on the right hand side. So, these would be the means. The remaining part of the x's are broken up into 2 components. One part is the part explained by the factors, and the other part is the error. Now, the factors are common to all the elements. So, we call them the common factor. The epsilons are specific to each of the variables. So, we call them the specific factors. So, what are the specific factors? For example, if you look at 2 languages like vernacular and English, and the student who is creative will be doing better in both of them. However, there would be a difference among these 2 subjects itself, probably because the student reads more vernacular books than the English books, and therefore, his or her score in vernacular might be higher. So, there would be some specific factors related to each of these variables, which are not common with the other variables. So, the general factors are f1, f2, fp, and the specific factors are this epsilon. We will be more concerned with the general factors, because we can reduce the number of variables by looking at the general factors, but the specific factors would not help us in reducing the number of variables. Next, let's look at the assumptions. So, we can write x1, x2, xm as a vector x, which is given by the vector mu, given by mu1, mu2, mu_m, and loadings are taken into a matrix L, and F again is a vector composed of f1, f2, fp. Epsilon is a m-dimensional specific factor vector or a error vector. The first assumption that we make are f and epsilon are independent of each other. Now, at this stage it should be interesting to look at the model and compare it with the regression model in general. In a regression model, we write the dependent variable y as x times beta, where x is the independent variables plus an error. If you take mu equal to 0 here, this model looks similar with the dependent variable y replaced by x here and the independent variable x replaced by f here, with L as the coefficient matrix or the betas. But however, there is one big difference in the sense that in this case, unlike in a regression where you know both the response and the independent variables, here only you have x, you do not know what f is. So, there is nothing on the right hand side that you know here. So, in this case, the whole of the right hand side is unknown, and that makes a real problem when we look at the factor model. Since whole of the right hand side is unknown, we can make this assumption that expectation of f is 0, expectation of epsilon is 0. So, that the expectation of x can be taken to be mu, so that we can always correct the observations by taking deviations from the mean. So, if you take x minus mu, that would be equal to LF plus epsilon. Okay. So, the second assumption that we make is covariance of f is equal to the identity matrix, that is the variances of the fj's are equal to 1 and the fj's are uncorrelated among themselves. So, the covariance is 0. It is a diagonal matrix with all the diagonal elements equal to 1. We assume that the covariances of the epsilon is equal to psi, which is a diagonal matrix. So, again what we are assuming, and this is very logical, is that the different specific factors are independent of each other, and more importantly, they may or may not have the same variability. That is, diagonal elements are non-zero and they may not be equal to 1. So, unlike for the f, we are not assuming that the variances of the epsilon j's are same. Now, in this case, it reduces to expectation of x is equal to mu and the covariance of x is equal to L prime plus psi. We will call this sigma. Now, this really means that if you look at the covariance between xi and xj, then it would be given by Li1 into Lj1 plus Lip into Ljp. So, it is basically the ith row of L and it is the product sum with the jth row of L. That would be the covariance. What about the variance? The variance will come out to be equal to Li1 square to Lip square plus psi I. It is basically the square of the elements in the ith row summed up, and with it the psi I factor would also come in. Now, what we do here is we can see that the variance of xi is broken up into two components. One is the components given by the loadings, and the second component is the component coming from the variance of the specific factors. The first component together, this is sum, is referred to as the communality, and the second component, the psi I, is referred to as the uniqueness. So, one part of the variance of x is explained together by the different factors, common factors, and hence we say that its communality, and the other is a unique factor given by the specific factor corresponding to the given variable. So, it is only unique to the particular variable we are concerned with. Communality is what we'll be more interested in rather than the uniqueness, and if we have a very good model where the common factors explain a majority of the variable, then we would be expecting that the uniqueness would be small and the communality would be the larger part of the variability. So, one part is shared by the factors and the other is the additional variability specific to a given xi. Now, before we move further, we just need to look at the condition that we have for f. We have assumed that the dispersion of f is I. This is generally referred to as an orthogonal model. There can be models dispersion of f is not a diagonal matrix. There can be of diagonal elements and we can have a oblique factor model, but we will not be considering oblique factor models here, because that would bring in a complexity which we are not at this stage to able to handle. So, we will just be looking at orthogonal models. Now, let us look at an example. In this example, we have 6 variables. These are 6 diseases. These are namely the cardiovascular disease, the cancer disease, the pulmonary diseases, pneumonia and diabetes and liver. And the data basically is the number of deaths owing to this diseases. And we wanted to find out if there was some particular factor or factors which actually which are common to all these diseases. So, we tried out a factor analysis with this 6 variables with the data on this each of these diseases for different states, and what we saw is that there were, of course, there were 6 factors that we could have taken, and the first factor actually accounted for about 35% of the variability, whereas the second factor was taking account of 25% of the variability. So, together the first 2 factors were accounting for 60% of the variable. You could go on to the third one, which was about 15% of the variability, the fourth one which would take it almost to the 90% variability, but we stopped with these 2 factors, and then we looked at what this gave us. The first factor gave us these loadings 0.974, 0.743, minus 0.271, etc. So, these are the coefficients in the combination of the factors. So, for the cardiovascular variable, call it x1, the model would be, if this is a centered model in the sense that we have taken out the mean, it will be 0.974 into f1 plus 0.121 into f2. Cancer would give us 0.743 into f1 plus 0.413 into f2. For pulmonary diseases, it is interesting in the sense that the second factor does not arise. So, what we now see is that how each of these factors influence each of the given variables. We can see at once that the pulmonary variable in this case has a first factor which is negative as compared to the others, and the second factor absent. So, this disease is different from the other 5, and even if you look at the other 5 now, so probably if you look at factor 3, the pulmonary would come in. It will have a high loading for factor 3, but it does not have a high loading common with the other 5. If you look at cardiovascular and diabetes, for instance, they have different factor loadings. For cardiovascular, the first factor has a high loading and the second factor a very low loading, whereas for diabetes is just the reverse. So, there may be 2 different reasons working for these 2 diseases, and this is how we can use factor analysis to assess the variables in terms of communality or commonness as far as their underlying structure is concerned. Today, we looked at the factor analysis model, and we saw that we can explain a large number of variables through a smaller number of factors which are common to these variables, and that way we can reduce the dimension of the variables. Now, one problem that we faced with the factor model is that when we write this model, nothing on the right hand side of the model is known to us. It makes estimation of the parameters difficult. Unlike the regression models, where the right hand side has the independent variables and hence we can use least squares, we cannot directly use the least square method here. So, we will be looking at techniques of estimation of the parameters, which are primarily the elements in L, the loadings, and the elements in Chi, the uniqueness factors. We will see how we can do this in the subsequent classes, and we will see how we can interpret those results as we go along.